Okay, so the other topic that we did want to cover, I'm really glad we're covering this one because this is a daily one I use. And for those of you going on, especially into more data science oriented fields, this is essential. We're going to go over basic, very, very basic integration. If you do anything more complicated, I actually don't recommend R. But also differentiation, finding roots, and then optimization functions. We'll see if we get to the rejective sampling methods. So integrate is the function that will integrate functions of one variable. You can, your interval can be finite or infinite. If you need a lower bound or upper bound that's infinite, just use the command capital I enough. The capital is important. The function you are integrating must have a vector argument and return a vector with that function evaluated at each point of your argument vector. So you can vectorize, use the vectorize function to perform vector computations. I'll need to show you this in the future if we do this. Integrate along with sapply will allow you to do multiple integrals. So remember, supply applies, the integrate will apply the integrate function over different components of a list or elements of a list, and then return it as a vector format. So it works for that reason. Okay, so you have to enter the function, the lower and upper limits. Pretty easy set of arguments. So for example, if our function is the e to the x, okay, then we define the function. Notice it uses the function, the user-defined function framework. You could put curly brackets around expx there, but it's not needed since it's only one line. Then you integrate with your lower limit, your lower bound being 0, your upper bound being 1, and it'll return this object of class integrate. You can get the estimator of the integral by using the $sign value. So usually I save this to a named object like I wouldn't use I though, generally. Name it something more informative. And then you can access that value estimate of the integration by using this $sign value. You can integrate normal density functions. So, we have p-norm, of course, but if you want to do something very much defined by you can use this. So we are integrating over the density, the normal density. You can go from negative 1.96 to positive. Of course, you get 95 there because it's standard normal. Or you can integrate across the entire density, so you get 1. You can define a function like this. So we have here our function g has the value 1. We can integrate from 0 to 1. Simple argument, right? But we need to vectorize g. So notice g from 1 to 10. Okay, so that's just going to give you 1 for any value, of course. So if we just do this, we get back 1. It's not really what we want, especially if we're thinking of g as being like a uniform, continuous uniform distribution or something. If we vectorize g, then we will get back, this command will give you a list of 10 ones because it's saying, I want to evaluate it at x equal 1, x equal 2, on up to x equal 10. And you get back 1 each time because that's always the result. That's always the result of that function g. But if we integrate across the vectorized version of g from 1 to 10, we're going to sum up all of those values across the density. So if we go from, let's see, 1 to 10, not including those boundaries, we should get 9 for that last argument. You can test that out and see. Numerical integration can also be performed. So for example, if we have a function with two variables, x and y here, we can integrate that function. Here we have the integral from 1 to 2 with respect to the function or variable y. So notice y is integrated from 1 to 2. We can tell here notationally because it's the order of integration is y then x. Okay, so we get back the value of that integral. Then notice that is embedded within another function which integrates that value with across the domain 0 to 3. So we're keeping that order of integration from 1 to 2 and then 0 to 3 by ordering the integrand in the proper way within the integrate function. Okay, so that just iterates through it. We can also integrate with respect to one of the variables in our expression doing the following. So here we have our inner integral. We are integrating from x to 1 across the function with respect to y. Okay, that's our order of integration is dy dx here. So we get back that value. Then we're going to integrate with respect to the entire domain 0 to 1, the result of that inner integral there. So now rather than integration, how you do differentiation, you can do symbolic derivatives within R. Here's your expression. This is going to be a formula. It can have no left-hand side if need be. You name your variable. So this would be a character vector giving the variable names with respect to which your derivative should be computed. And then a true-false of whether or not you need that Hessian. Okay, that's up to you, whether or not. Computationally, it's easier if you don't compute that gradient matrix. Okay. So taking the derivative of x squared with respect to x, here we want the Hessian, okay? So here's, if you ran this, you'll see the argument or the result in here. Here we create a vector, x 1 to 5. We're going to evaluate this expression for those values, x equal 1 to 5, and put them in this object dx.num, and this will then have the attribute, we then assign the attribute gradient as the gradient vector. All right, so this is one fairly simple example. Here's another that has two variables, x and y. Notice here we're using the expression command rather than the formula up here. And save the result in here. Then we create vectors for x, vectors for y. We evaluate the result of that derivative and assign it to be a Hessian, because this will be a matrix, right?